Hey, welcome to Minute Science Marvels. Skip the first minute if you don't want to hear me yap, but I have to get sappy real quick. First off, I so appreciate every single one of you who have already followed, subscribed, interacted with my stuff. You guys will always hold a special place in my heart because you were here when I was just kind of figuring things out and testing the algorithm, seeing if my shitty jokes will land. But now that I've had some practice speaking, editing, and making content, I feel like I'm finally getting my footing. Right now, I'm recording a Zoom meeting because I don't know how to do the green screen background situation. But I still think there have been leaps and bounds. I'm at the point where I look back at last week's content and I cringe a little already. But now we're getting started with a structured solar system series with a predictable format so I don't have to keep kind of pulling topics out of nowhere and hoping that they stick. As much as I'm a yapper, I really hate bullshitting, and everything just felt like so much more of a task than it needed to be because planning was half the battle. So now we're actually getting started. We're going through the solar system and we're starting with a redo of the first ever episode. If you want to look back at the old one and laugh, it's still going to be up, but all of the information and more is in this video now. We're talking about the sun, the star that makes life on Earth possible, but could also completely wreck us with a single solar storm. Let's get into it. For as long as humans have existed, the sun has been a mystery, a god, and the center of life. Ancient civilizations didn't see the sun as a bright ball of light. They saw it as a powerful deity. The Egyptians worshipped Ra, the sun god, as the creator of life. The Aztecs believed that the sun god needed constant human sacrifices to keep shining. And the Greeks thought that Helios, the god of the sun, literally rode a flaming chariot across the sky every day. At first, humans thought everything revolved around the Earth. This is the geocentric model. Ptolemy in the 2nd century supported this idea, and it lasted for centuries. Then came Copernicus in the 1500s, who shook things up by proving that Earth wasn't the center of the universe, the sun was. This is called the heliocentric model. Galileo followed this up with telescopic observations to back that up, but of course, that caused a major controversy, especially with the church at the time. The Catholic Church, which strongly supported the geocentric model, saw the heliocentric model as a challenge to religious doctrine. In 1616, they banned Copernicus's book and put Galileo on trial for hearsay in 1633. He was forced to recant all of his findings, and then he spent the rest of his life under house arrest. Despite this, his work laid the foundation for modern astronomy, and then centuries later, the church finally acknowledged that Galileo had been right all along. The heliocentric model not only changed our view of the universe, but it also paved the way for modern physics and astronomy. Kepler refined it with the discovery of elliptical orbits, and then later, Newton's laws of motion solidified how gravity governs planetary movement. Okay, so that's the semi-short history, but for a little more background, where did the name sun actually come from? Here's where you might have to forgive my pronunciation. The name sun comes from the Old English word sunnen, but the Latin name sol is where we get terms like solar system, solar flares, solar energy, solar everything. The first recorded use of sun in English dates back to the 10th century. In ancient Rome, they referred to it as sol invictus, which means unconquered sun. Most languages have some variation of sol. Spanish and Italian, it's just sol. In French, it's soleil. In Russian, it's sonce, and so on. The earliest written records of humans referring to the sun date back over 4,000 years in Sumerian texts. But now that we've got the history out of the way, let's get to the science, starting with its place in the solar system. So the sun isn't just at the center of the solar system, it's the gravitational anchor that everything else orbits around. With over 99.8% of the total mass of the solar system, it controls the motion of every planet, moon, asteroid, and comet. All of that mass creates a huge gravitational pull. But gravity alone doesn't explain why things don't just fall into the sun. Each planet is also moving sideways at high speeds because of the momentum that's left over from the swirling disk of gas and dust that formed the solar system billions of years ago. The combination of the gravity pulling inward and then the momentum from the sideways motion pushing forward results in the stable orbits. But these orbits aren't perfect circles, they're ellipticals. The shape of one depends on each planet's speed, its distance from the sun, and its interactions with other bodies. The closer a planet is to a sun, the stronger the gravitational pull feels, and the faster it has to move to stay in balance. That's why Mercury just zooms around the sun every 88 days, and Neptune takes 165 years to go around one time. Of course, this is all in comparison to Earth's definition of a year, which is the amount of time we take to do an orbit. But it's not just planets that orbit the sun. Lagrange points are gravitational sweet spots where objects can stay balanced between the sun and a planet's pull. We place satellites and observatories at this point, like the James Webb Telescope at L2. I'll find a picture that explains this a little better if you're on the audio version. Really sorry. What else though? The sun also plays a huge role in Earth's climate system. Sunlight heats the Earth, but it does it unevenly, with the Earth receiving more of the direct radiation than the poles, the North and South Pole. That temperature imbalance creates atmospheric circulation. Warm air rises, cool air sinks, and that drives weather patterns, jet streams, and the Hadley cells that circulate air around the globe. It also heats the oceans. This creates currents like the Gulf Stream, which move massive amounts of energy and also directly influence weather. But what would happen if the sun just disappeared? Within seconds, the gravitational balance of the solar system would totally break and Earth would just fly off into a straight line. Within hours, Earth's temperature would start dropping. Within a week, it would be below freezing. Within a year, it would be around negative 100 degrees Fahrenheit. Photosynthesis would stop, ecosystems would collapse, and only a few microbes and super creepy deep sea creatures living near the hydrothermal vents would keep going. And the weirdest part is we wouldn't even know for 8 minutes and 20 seconds because that's how long the light takes to reach us. So even if the sun just blinked out of existence, everything would seem totally fine for 8 minutes. Then darkness and chaos. Zooming out even further, though, the sun creates a giant protective bubble around the solar system called the heliosphere. This is formed by the solar wind, which is a constant stream of particles, mostly electrons and protons, that flow outward from the sun in all directions. The boundary where solar wind slows down and meets interstellar space is called the heliopause. It's like the edge of the sun's personal force field. The solar wind also carries Lyman alpha emissions, a type of ultraviolet light that interacts with hydrogen in space. Scientists use these emissions to study not just the structure of the heliosphere, but also to detect exoplanets, analyze atmospheric escape on distant worlds, and to understand how stars affect habitability. A cool thing about the heliosphere is that it's not a perfect bubble. It's shaped more like a comet with a long tail that stretches behind the sun as it moves through the galaxy. I thought that was awesome. I always just pictured it as a sphere. But my favorite solar effect the sun has is auroras. I definitely have a whole spiel on those later. The short version is if you've seen the northern or southern lights, that's also part of the sun. So yeah, the sun is constantly shaping our orbit, our climate, our visibility of the stars, and is the literal edge of what counts as our part of space. But how old is it? What's it made of? And what's it like over there? So the sun is approximately 4.6 billion years old, and that's considered middle-aged for a star of its type, which is a G-type main sequence star, also called a G-dwarf. This classification indicates that it's in a stable phase of hydrogen burning when it's converting hydrogen into helium in its core. This process releases energy that powers the sun and provides the warmth and light that is essential for life on Earth. The sun's diameter is about 109 times that of Earth, and its mass is approximately 330,000 times greater. Again, it's about 99.8% of the total mass in our solar system, meaning that the planets, moons, asteroids, comets, everything else combined is zero point 0.2. Wild. But it also constantly loses mass due to solar wind, about 4 million tons per second. Solar wind is when the sun ejects charged particles, mostly electrons and protons. These particles escape because the outer layers are so hot that the kinetic energy overcomes the sun's gravity. Despite these mass losses, it's only lost about 0.05% of its original mass over the past 4.5 billion years, which is nothing. Between bloating and food, my mass fluctuates like 5% on the daily. The mass that there is made up mostly of hydrogen, just under 75%, and helium, which is just under 25%. The rest of that 1 to 2% is heavier elements like oxygen, carbon, neon, and iron. Those elements are crucial for the formation of planets and life as we know it. The sun itself has several layers, each with distinct characteristics. In the middle, of course, there's the core. That's the powerhouse, that's where nuclear fusion occurs, where it converts hydrogen to helium and releases energy via Einstein's E equals mc squared equation. There's an older episode on fusion if you're interested in that process specifically, but the quick version, if you're thinking of Chernobyl or nuclear power plants, it's the opposite. Those are fission, which splits atoms apart. This, what the sun does, is fusion, which we haven't quite figured out as a larger scale power source. Like the name implies, this is when two atoms fuse together to create a larger nucleus. But yeah, sorry for the side note. After the core is the radioactive zone. Here, energy moves outward slowly, taking thousands to millions of years to reach the next layer, which is the convective zone. Here, hot plasma rises and cooler plasma sinks, creating massive convection currents. Kind of like what happens when you boil water. Bubble rises from the bottom where it's the hottest, and then the cooler water sinks down to take its place. Then, outside of that is the photosphere, which is the visible surface of the sun. That's where light is emitted. Then there's the outer layers, the chromosphere and the corona, which are hotter than the surface of the sun due to still mysterious heating mechanisms. The corona can be 1 to 3 million degrees Fahrenheit, while the surface is 10,000 degrees. That's 2,700 times hotter. To put that into perspective, that's like comparing something at room temperature to like a raging fire, or that same fire to the heat of a lightning bolt. I love that fact. So, we know what the sun is made of. But what does it look like, and how does its magnetic activity impact us? So to start off with color, the sun isn't actually yellow, it's white. It only looks yellow from Earth because our atmosphere scatters shorter wavelengths like blue and violet, which leaves behind the longer ones like red and yellow. But if you viewed it from space, or even just a planet that doesn't have much of an atmosphere, you would see its true color, pure white. That's because it emits light from across the full visible spectrum. For Mercury, where there's essentially no atmosphere to scatter the light, the sun is white and it's blinding because of how close it is. From Mars, where there's a thin carbon dioxide rich atmosphere, the sun is tinted blue. And then from Saturn and beyond, it doesn't really dominate the sky like it does here. It just looks like a really bright star because of the distance. Even though it looks calm from the Earth, the sun is constantly churning with magnetic chaos beneath the surface. It's a constantly shifting ball of charged particles, and that motion creates powerful magnetic fields through a process called the solar dynamo. Inside the convective zone, hot plasma rises and sinks in looping currents. Add the sun's rotation to that, and now the magnetic field lines are getting twisted, tangled, and stressed. That tension builds and builds until it snaps. And then you get sunspots, cooler, darker patches on the surface. But the sunspots are just the start of the action. The sun's intense magnetic activity causes solar flares, sudden powerful bursts of energy that release massive amounts of radiation and charged particles into space. Think of them as like the sun's version of a volcanic eruption, but instead of molten rock, it's pure energy shooting out at incredible speeds. Then there are coronal mass ejections, or CMEs, which are like solar flares on steroids. These giant explosions can hurl billions of tons of solar particles through space, traveling at speeds of 1 million miles per hour. To give you an idea, one single CME can carry the energy equivalent of billions of nuclear bombs. And if you're an aurora chaser, this is your moment. When a solar flare or a CME hits Earth's magnetic field, it sends a shockwave of charged particles spiraling towards the poles. These particles slam into our atmosphere and excite the gases, which are what create powerful, colorful waves of light in the sky, auroras. On Earth, we mostly see greens and reds because of oxygen and nitrogen, but on Jupiter or Saturn, you'd see blues and purples because their atmospheres are full of hydrogen. And on Mars, there are no global magnetic fields, so auroras can happen basically anywhere, all across the planet. But yeah, next time you see those really cool photos, you know they started with that weird magnetic twisty snap 93 million miles away. Right now, we're actually in a solar maximum, which was expected to peak in 2025. This means that we're seeing more solar flares, CMEs, and auroras. Some are even showing up as far south as Florida. Naturally, the internet ran with it. If you've seen posts claiming that it's the apocalypse, global warming, something crazy, that's what that's all about. In reality, it's just the sun doing its thing. The solar maximum is the most active phase of its cycle, and while it can cause some tech disruptions, it also gives us incredible aurora displays, sometimes in places that we rarely ever see them. So, not quite the end of the world yet. One of the biggest mysteries of the sun might be related to the magnetic activity. We'll kind of talk about this when we go through the research, but the corona, the sun's outermost layer, is somehow millions of degrees hotter than the surface. Scientists think that magnetic reconnection, which is when those twisted field lines snap and release energy, might be the key. But it's still an open question, and figuring it out matters because the same forces that drive this activity can also affect our satellites, GPSs, power grids, even astronauts. But let's take a pause from the technical facts. I'm an overthinker, so I love going through all the possible hypotheticals. We learned about the conditions, magnetic activities, composition, but what would happen if we actually go to the sun? All right, so there's the temperature. Even if you're on Mercury 36 million miles from the sun, the temperatures there can reach 800 degrees Fahrenheit during the day. You'd last maybe 2 seconds before your eyeballs boiled and your blood started to cook. But okay, let's say you're in a heat-proof suit, not just heat resistant, heat-proof. You keep going. You approach the corona, which is the outermost layer of the sun. Again, here it's over 1 million degrees Fahrenheit, and you're getting bombarded with ionized particles and radiation. Here, space itself is hostile. Your suit is gone. You are vaporized. But let's pretend you're immune to heat somehow. Now you're passing through the photosphere, which is the visible surface of the sun. Here, the temperature drops down to 10,000 degrees, weirdly, but the intensity of the light and the energy is unreal. You're moving through blinding plasma that's so thick, it's like a molten fog. The sun's gravity is 28 times stronger than the Earth, so you're being pulled down fast, like you're getting squished into a human pancake. Say you're also pressure-proof now, me. Now you're inside the sun's convective zone, where there are churning currents of plasma flowing in chaotic loops. It's like getting stuck inside a lava wave pool during an earthquake. And you have nowhere to land. The sun doesn't have a surface. You're just sinking deeper and deeper into a sea of charged particles. Oh, and radiation. Gamma rays, X-rays, high energy particles, stuff that'll rip through your DNA like a paper shredder on overdrive. But fine. In this scenario, we're going to be radiation proof too. Eventually, you slow down and come to a rest somewhere deep inside the radioactive zone. Light created here takes thousands, sometimes millions of years to escape. So you're not dead, you're just stuck. You're floating in like a glowing soup of hydrogen fusion. So I guess that's where we'd stop. You would need to be fireproof, crush-proof, radiation-proof, have no need to breathe, and also be okay with an eternity of being lost inside a nuclear starstorm. Not even Goku could pull that one off. But enough hypotheticals. Let's talk about what's actually happening now in space science, because we are in an incredibly exciting era for studying the sun. There's NASA's Parker Solar Probe. Launched in 2018, NASA's Parker Solar Probe is the closest we've ever come to actually touching the sun. And kind of literally, it's flying through the sun's outer atmosphere, the corona. The probe is designed to withstand speeds of 430,000 miles per hour, which makes it the fastest human-made object ever. Its mission is to answer some of our biggest questions, including why is the corona hotter than the surface? Where do the solar winds actually come from? And how solar energetic particles accelerate so quickly, sometimes reaching Earth in under an hour. To get this close, Parker is using 7 Venus gravity assists to gradually shrink its orbit. In December 2024, it broke records again by coming within 3.8 million miles of the sun's surface. The data that it's collecting is already transforming our understanding of how energy and particles move through the corona. But meanwhile, the European Space Agency, ESA's solar orbiter, which was launched in 2020, is taking a different angle, literally. It's observing the poles, something that we've never done in detail before. But why does that matter? The poles are the key to understanding the solar dynamo, the engine behind the sun's magnetic field. Solar Orbiter is equipped with 10 instruments, including cameras and sensors that measure solar wind plasma, magnetic fields, energetic particles, and UV and X-ray emissions from the sun's surface. Together, both of these missions are covering all of the bases. Parker is diving into the fire, and Solar Orbiter is hanging back, taking wide shots and tracking the whole system as a whole. And the collaboration is working. Data from both is already helping refine our models for predicting solar storms. But there are also some other cool missions that you should maybe know about. There's Proba 3, which the European Space Agency, ESA, just launched, which will fly 2 satellites in perfect formation to create artificial eclipses. This will allow us to have continuous observations of the sun's corona without waiting for a natural eclipse on Earth, because those are not that frequent. Aditya L1, which is from India's ISRO, launched in 2023. It's positioned at Lagrange point 1, where it can constantly monitor the sun without Earth getting in the way. It's measuring solar radiation, solar wind, and magnetic fields, which are especially useful for early warning systems for solar storms. There's also SOHO, the Solar and Heliospheric Observatory, which is a collaboration between NASA and ESA, which has been observing the sun since 1995 and was key to discovering how CMEs affect Earth. Another one is the SDO, the Solar Dynamics Observatory, which launched in 2010, which takes high-res images of the sun in 10 different wavelengths. It's the one behind those beautiful extreme ultraviolet videos you've probably seen on NASA's Instagram. And there's the Daniel K. Inouye Solar Telescope in Hawaii, which is now the most powerful solar telescope on Earth. It can observe features on the sun as small as 12 miles across, which helps us study the fine-scale magnetic structures in unprecedented detail. But yeah, that's pretty much everything. And a big topic that's pretty current in research is the biggest unsolved mystery of the sun. Why is the corona so hot? Again, the surface of the sun is around 10,000 degrees Fahrenheit, but the corona is in the millions of degrees. That's like lighting a match and having the flame be colder than all of the air around it. It doesn't really make sense. There are 2 main ideas. The first one is magnetic reconnection. Magnetic field lines twist and snap, releasing bursts of energy that heat up. Another idea is wave heating. Waves generated inside of the sun rise and dump energy into the corona, kind of like ocean waves crashing onto shore. Both Parker and the Solar Orbiter are collecting data to help settle this debate, but right now, it's still one of the wildest open questions in astrophysics. But why does all this matter? We've talked about auroras, but on the extreme end, solar storms can get dangerous. In 1859, the Carrington event caused telegraph wires to spark and fail. If something similar happened today, it could disrupt satellites, GPS, aviation, internet. It could knock power grids out for days or weeks. These missions are really cool and they give us awesome insights and fun facts, but they're also essential. They help us understand, forecast, and maybe one day protect ourselves from one of the sun's angrier moods. All right, so that's pretty much everything, but now for the random fun facts that I didn't really know where else to put. But maybe they'll come up on trivia night, or you can use them to pick up someone. I don't know. Let me know how that goes. But the first one, You can fit 1.3 million Earths inside of the sun. But since it's mostly hydrogen and helium, its density is still overall lower than the Earth. We kind of already mentioned this, but a strong enough solar storm could cause trillions of dollars in damage if it hit Earth today. Satellites, GPS, planes, power grids would all just be fried. The sun is middle-aged. It's about 4.6 billion years old, with another maybe 5 billion to go. I might have word vomited that earlier, but yeah. Eventually, it'll expand into a red giant, engulf Mercury and Venus, maybe even Earth, and then it'll shrink into a white dwarf and then slowly fade away. One of my favorites, the sun isn't solid, so it doesn't spin uniformly. Its equator rotates in about 25 days, while the poles, the upper and lower, take around 35 days. That difference creates the magnetic tension and contributes to all the twisting that we see. Another thing is, the sun's gravity can bend light. Einstein predicted it, and it was first proven during a solar eclipse in 1919. It's like the sun is messing with the laws of physics. The sun is also moving, and it's moving fast. It's barreling through the galaxy at around 450,000 miles per hour, dragging the entire solar system with it in a massive spiral orbit around the Milky Way. And, do you hear that? The sun has a soundtrack. It vibrates like a giant instrument. NASA converted those sound waves into actual audio and it hums. But yeah, if you made it to the end, wow, that's amazing. Thank you so much. But yeah, the sun is really cool. The sun is really hot. It's incredible. It's literally giving everything to us. But one day it'll expand into a red giant and maybe possibly swallow the Earth whole, so I guess enjoy it while you can. The current plan after this is to go in order of the solar system. So next week, I'll be back to yap about Mercury forever. If you have any questions, please, please, please ask. I'd like to think I'm fairly good about answering in the comments. And then if they require more than the character count, I can make one of the YouTube shorts, TikToks, whatever. But yeah, please like, subscribe, comment, download, do all the things, and I'll see you next Thursday.